Hey everyone, Structure Pro, another example here. So we're going to be going over the graphical relations method this time, as I like to call it. And this is a method that we're using to construct shear force and bending moment diagrams. So I've written our sign convention that we're going to be using, as well as these relationships that we derived in previous videos that are always so important. So step one, as usual, let's start off by finding the reactions for what we're given here. So we're going to call those BY and AY. And first step, it's easiest to start off with summing all the moments, because that way you can actually get one of the reactions. So we're going to sum them about A, with counterclockwise being positive. I'm just going to skip ahead a little bit here, because we know what we're doing here, folks. So after all the heavy lifting is done, we're going to end up with BY of 2.25 kilonewtons. Let's write that in there. Then summing all the forces, vertical forces, equal to 0, come up with AY is 9.75. If you want to check, you can sum all the moments about B, and it's going to come out to 0. All right, nice work. Feeling good. Next, we're ready to assemble our shear force diagram. And this very convenient method that we're about to use really just involves visualizing the forces that the beam is exposed to, pushing and pulling the shear force diagram up and down. So let's start off with this reaction AY. It is acting upwards on the beam, so we can almost feel it happening. Push up the shear force diagram, the same value that it is, up to 9.75 kilonewtons. Then we're going to look at this distributed load. We see that the area under it, 3 kilonewtons per meter times 4 meters, is 12 kilonewtons. We know from our relationship on the right that that's going to be equal to the change in shear over that same 4 meter span. So we know 9.75 minus 12, negative 2.5. We can connect them directly with a line. We know this is linear because it's essentially one order higher than the loading was. For this case, the loading was constant. Then we note there's no more forces from C to B, so we're just going to keep a straight line right across, and then again, the diagram is going to be pushed up by the value of BY at the support B. And we're unaffected by that moment at the end. That'll affect the moment diagram, but it doesn't affect the shear diagram. Well, it does when you consider that it changed what the reactions would be, but it doesn't have a local effect where it's happening. Okay, so great work on the shear diagram, folks. Now it's time to figure out the areas. Let's call them A1, A2, and A3. The reason we're figuring out these areas, because if we look at this relationship here, the dm over dx equals vx, we can integrate both sides, and then we get mx is the integral of vx. So this is really saying that the area under vx, or v, is the change in moment, okay, between 2 points. So let's start off by getting area number 1. First thing we have to do here is actually find out what x is, x being this base of the triangle. We know the height of it, 9.75 kilonewtons, but we need to know the base of it. So in order to get that, we actually use the slope of this line, which, looking up at the distributed load and remembering how we constructed the line, the slope is, for every 1 we go across, it's down 3. So you all remember rise over run, but don't worry, we won't get into that. We'll just use this simple equation, knowing that we have to go across a certain number, x, and we're going down 3 every time. We know that 3x equals 9.75 kilonewtons. In other words, x is 3.25 meters. So we'll fill that in right down at the bottom there, and then we can write out what our area number 1 is. So area number 1, we're going to take, our basic triangle equations, the width times the height divided by 2. So 9.75 times 3.25 divided by 2. We're going to end up with 15.884 kilonewtons. So this is the change in moment over that distance. And it's a positive area, we know. So that means the moment's going to be getting larger. So area 2 should be easy for us. It's just that 4 meters subtract the 3.25, and then we're going to multiply this. This time it's negative 2.25, and then we're going to divide that all by 2. We get area 2 is equal to 0.884 kilonewton meters. That means that's the change, a negative change in moment over that span. Area 3 is a super easy one, but my drawing skills are kind of lame, so got to give it multiple tries just to make this simple box. Sorry, guys. Okay, yeah, so a very simple one here. It's just a rectangle. If you can't figure out the area of a rectangle, I'm sorry, folks. You've come to the wrong video. So negative 2.25 kilonewtons times 4 meters, we're going to end up with 9 kilonewton meters. Notice the units of these three areas, kilonewton meters. Rings a bell, right? It's actually the same units as for the moment diagram, so the units always work out, folks. Wow, I'm saying folks a lot today. That's kind of weird, because I'm not a hillbilly. Oh well, so we're ready to construct our moment diagram now that we have all these areas under the shear diagram. And this is going to be simple. We know the moment starts at 0, because that's a pin support. So it's just a matter of adding up these areas and subtracting them in the end. So we're going to start at 0. We're going to go up. We're going to rise this positive 15.884. And we don't actually know what type of shape we're going to draw between the 2 points. For that, we have to look at the shear diagram. We see the shear diagram is linear over that portion. Because we're integrating, we're going to add an order, basically. So linear first order plus 1 is parabolic second order. And the slope has to end at 0 because we know the value of the shear diagram is 0. So parabolic second order, and we're going from 0 to 15.884. And then we're dropping how much? This negative 0.884, right? So that brings us down to 15. So we can fill that in. There we go. Label our points. Fill that in. You got to be very careful drawing these parabolas. They're tricky ones. Okay, then from a value of 15, what are we going to do? Well, A3, I've written 9, but I left out the minus sign. Oops, sorry, folks. Wow, folks again. Anyway, so negative 9 kilonewton meters. So we're going to drop from 15 minus 9 all the way down to 6. And that's going to be a straight line, right? Because the shear was constant over that region. So that means the slope of the moment diagram is constant. In other words, linear. And would you look at that? The 6 kilonewton meters is going to take the rest off our hands. And wow, I'm having a bad day here, folks. I labeled that 9. That should be a 6. Don't worry, I prepared the solution ahead of time for the case of this exact eventuality that I inevitably screwed up. Okay, so here we go, the big reveal, the solution, and we see that we were mostly correct. There we go. The one thing I want to point out is that I've labeled the curvature of the moment diagram. So rather than relying on positives or negatives, it's sometimes nice to actually put the curvature. And we can tell from the loading that this is the way the curvature is going to be, right? So I've just circled that in red. So yeah, anyways, questions or comments below. Pause the video if you had a question earlier on, if you need to take a closer look. Thanks for watching. Peace out and keep practicing.